In today's lesson, we're going to look at the integrated rate law. So far, we've talked about the rate expression and we've talked about the differential rate law. So in this lesson, we're going to look at the integrated rate law. The integrated rate law is going to be using concentration versus time data rather than concentration versus rate data. For each order that we're going to study first, second, and zero order. Each equation is in the form of the slope-intercept formula, where we have y equals mx plus b. Now, in order to determine the order of your reaction, we must perform a linear regression. So a graph of y versus x is what we're going to be plotting. And we will verify which plot reveals a straight line with the appropriate slope. I do want to remind you that to solve for slope, you take the rise over the run. So the change in the y value divided by the change in the x value, or y final minus y initial divided by x final minus x initial. So for first order integrated rate laws, what that means is that if the concentration of the reactant is doubled, then the rate of production of the products would also double. So far in this unit, we've determined that for a reaction where you have little a being your coefficient from the balanced equation times, and compound A here will be your reactant A, yields products. If you're looking at that as your equation. If it were first order, we've talked about how to find your rate expression. So that will be equal to negative, because reactant concentrations decrease over time, negative 1 over A, so the inverse of the coefficient, times the change in concentration of A over the change in time. So this is your rate expression coming from the definition of rate. And also, if you were to consider the differential rate law that we determined using method of initial rates, if it were first order from our calculations that we did yesterday, we would write the differential rate law would be equal to rate equals k times a to the first power, first order. So the corresponding integrated rate law is natural log of a times, or natural log of a at time equal to t equals negative kt plus the natural log of the initial concentration of reactant A. So again, this is the natural log of A at time equal to t. K is your rate constant, which is also going to be your slope here because it's going to be in the form of y equals mx plus b. Keep that in mind. The x value is always your time. So y versus x, natural log of A versus time. And notice it has a negative slope. So when you graph this, you would see it would have a negative slope if it were to for sure be a first order integrated rate law. And the y-intercept would be equal to the natural log of the initial concentration of reactant A. So if a reaction is in fact first order, a plot of y versus x, again, y is natural log of A at time equal to t versus time, would reveal a slope that's negative, as you see here depicted in this graph, and the y-intercept equal to b. So on the graph, we would have plotted natural log of A on the y-axis, and time would be plotted on your x-axis. I also want you to be able to determine the half-life of these reactions. So for a first order reaction, half-life will be calculated using this formula. The half-life is equal to 0.693 divided by K. Now remember that half-life represents the amount of time that it would take for 1/2 of the previous amount to disappear. Now you'll notice with the first order half-life formula, it only depends on the constant, the rate constant. I will give you these half-life formulas. You do not have to memorize them. Second order integrated rate laws. What this means if it's second order is that if the concentration of the reactant is doubled, then the rate of production of the products would quadruple. So far, again, considering this as our reaction, if it were second order, we could write the rate expression. Rate is equal to -1/A times the change in concentration of A over change in time. So the rate expression stays the same for this reaction. But if it were in fact second order, the differential rate law would have been determined again by using the method of initial rates. Rate is equal to K times concentration of A squared. There's your order, second order. So the corresponding integrated rate law for a second order reaction looks like this. 1/A, concentration of A at time equal to T, equals positive KT, so this will have a positive slope, plus the 1 over the initial concentration of A, or the inverse of A. T again is your time, which is going to be your X value. The Y value here is going to be 1 over concentration of A, and again the Y-intercept is the inverse of the initial concentration of A. If the reaction is second order, a plot of Y versus X, 1 over A versus time, will reveal a straight line with a slope equal to M. It will be positive in this case, and the Y-intercept of B. The half-life of a second-order reaction is calculated by using this formula, and again, you will be given your half-life formulas. The half-life is equal to 1 over K times concentration of A initial. So in this case, the half-life is dependent on the initial concentration for a second-order reaction. In our next video, we will look at the zero-order integrated rate laws.